if you recall in the previous class, what I told was, I told you what is a forward pass, and I told you about back propagation also, which is also called backward propagation. Okay. And this forward pass and backward pass helps to update our weights. I gave you a high level intuition how this weight gets updated, right? We still haven't gone to the mathematical detail of it. Gradually, I'll take you to that level, because if I directly show you the one go, you'll start hating deep learning. Trust me, that happened with me for a while. That's why I wanted to take you there gradually. And after completing the back propagation part, almost this deep learning journey will come to an end. After that, it will be all about applications, right? So let's go one level deeper into this, right? About the learning algorithm. In your screen, you see there is a neural network which is consist of two hidden layer, one input layer, and there's a one neuron in output layer. Okay. So initially, what we do is we initialize our all the weights and biases by some random values, right? Then what we do a forward pass. We compute our y hat. We compute our loss, right? And what we do a back propagation of this loss function, right? What we do essentially in back propagation is we compute the derivative of loss with respect to all the weights. We compute this dl by dw, dl by db, right? And once we compute this one, we update our all the weights and biases like the way we did in case of sigmoid neuron, right? This is a general high level understanding of computing the weights and biases, right? We all are clear at this till this point. Okay. Now here you'll see that, see, if I want to update the weights of all of my biases, weights and biases which are here at this point. So what are my weights and biases here? W111. This will be what? W112. Likewise, I'll have a total n cross n weight. If I'm assuming that there are total n number of neurons, and I'm assuming that there are n number of neurons in my input layer. Okay, so you'll have total n cross n number of weights, right? So what I'm doing is I am writing this derivatives in form of a matrix, because that will help to me to do computation in one go, right? So what I'm having, all the weights which are between this first hidden layer and my input layer, I'm writing here this and this, right? So you see dl theta, which is nothing but the partial derivative of loss with respect to this weight, then partial derivative of loss with respect to this weight, and it will continue till this weight, which is partial derivative of my loss with respect to 1 n. What is the weight of this? This is 1 n, right?
But you are written there 1 n1, right?
Where
In the matrix.
this is 1 n, right?
Oh, sorry. So we are going like column wise.
Yes, right. So
And
similar.
can you just remind me the nomenclature that we are following for the scene one? First value represents the neuron number, right?
First is the layer 1.
Okay, layer
Okay.
1, then input 1.
Yeah. So here, just a slight correction here. It is okay. Okay. Before I get to the correction point, let me tell you the nomenclature part first. W, then layer, then it was the output neuron. So when I say output neuron, I mean the hidden one, destination neuron, you can say, and then source neuron, right? So what source, it is coming from this point, so it is a source neuron. Yeah. Just think about that arrow sign, right? So this is my destination and this is my source. Okay.
Yeah.
And what I have done nothing. I have just arranged all my weights and biases in form of a matrix,
Okay.
right? For all this weights. Okay, so that if I do implement in a Python, I want every weights to be get updated in one go, right? It's just that I have followed this notation for updating all of my weights at one go in form of a matrix,
Yeah.
right? And this updates will happen with the help of this PyTorch or TensorFlow or Keras framework. Okay, PyTorch is also another framework like Keras we have.
So this update is happening only on that particular layer, right? At once. It is not happening on the other layers.
It is happening for all the layers. You'll see that weights and
Oh,
biases for all the, so you think this weight, this is this one, right?
yeah.
This is W211, right?
Yeah.
Okay, so in every iterations your value of weights and biases are getting updated. Okay, and at every node, every neuron, you need to compute the derivative of loss with respect to your weight, partial derivative of loss with respect to weight. Okay, all right. Now I'll just give you some mathematical brush up if you have, if you have forgot about the derivative part, because I think the last time when you would have seen this derivative, probably it would have been in your engineering classes. So I'm not going to explain how I am computing this derivative part. This is slide just for your reference. I would share this one, and please go through this basics fundamental derivative. This is the in many textbook, these are offered as a standard formula also, right? But the point which I wanted to feel comfortable is the chain rule in derivative. So before you come to the next class, please make sure that you are comfortable with chain rule. Okay, and what I meant by chain rule is, you see here, right? So this is I'm applying a chain rule here, right? So I'm not going to explain how we are computing derivative. It's very elementary. Uh, but I want you to be comfortable with derivative part. Okay, so when we see the math heavy part, you don't feel like lost in that class. Okay, and it's absolutely fine even if you don't bother to know the mathematical detail of it. Nobody is going to ask you. Okay, okay. Now
So what was the purpose of that slide that you showed?
because regardless of anything, I'm going to explain you backpropagation algorithm in detail.
Yeah.
Okay, so in that class I'll be talking about derivative. In that class I'll be talking about math part in detail. So these are the elementary concept required to understand the fundamental of that class. That's why I'm showing it to you beforehand.
So we need to like understand this. You're saying like whatever we are seeing here in
Yeah,
order to understand the next class.
yeah, you need to know. For example, in the next class, if I do the derivative of d e raised to x raised to 2 with respect to x, I'll not going to explain you how this derivative is getting computed. I'll directly write this one. The derivative of this is this,
Okay. Okay.
right? Like you must have been in your engineering class, right? The derivative of x square is 2x.
Yeah.
So I'm not going to explain that how I'm getting this x square derivative as 2x.
Okay. Got it.
Yeah, so that's why I'm bringing this slide in at least one class before that, so that you get comfortable with this. Okay. All right, but still let me give you a very high level glimpse of what I meant by saying a chain rule, because chain rule is very important, right? So let's say that this L theta is my loss. Okay, and I want to update my this weight W1 uh, 121. I want to update this weight. Okay, so what I need is, I need to compute this L theta with respect to W121, right?
Yeah.
Now see, I cannot directly compute L theta with respect to weight 1 to 1, because there are so many neurons in between this, right? And this effect we are seeing in loss is not just because of this particular neuron. It is having the effect of this neuron also, this neuron also, this neuron also, right? Because in order to compute this, there are effects coming out from this neuron also. So for that, what I can do is I can do dl. I'm just simply writing dl instead of writing dl theta, right? Then dw, and I am writing just no, here I need to write completely. Okay, now d y cap d h2 d h2 d h12 d h12. This is called chain rule. 1 2 1. Okay, am I missing anything? No. This is a chain rule. Okay, so see what I want to compute dl by dw12, right? So I can write in this form. So what I'm saying that this derivative at this point, it is, first of all, you are doing back propagating, right? So so whatever thing I'm getting here, it is coming out from here, right? Whatever I'm seeing here, the output of this neuron, it is having the effect of this neuron.
Yeah.
And
But are there outside two neurons? Like after y cap, there is one more neuron.
yeah, see,
But why, like y cap looks like the output, final output, right? Why do you have one more
no,
neuron?
this is not y cap. This is the here, after here I'll getting y cap.
But you wrote there y cap, right? So okay.
Okay,
Yeah.
okay. So this y hat, if I see this loss computation, if I see, it is having the effect of this neuron. This neuron is having the effect of this neuron, and again this neuron is getting the input from these three neuron,
Yeah.
right? And this neuron is getting the effect from these three neuron, right? So if I want to compute my derivative of loss with respect to this particular neuron, right, I need to traverse backward. So what I'm doing here is I cannot directly compute the derivative of loss with respect to this neuron. I have to travel back through this two neuron. So I'm going, first of all, I'm going this point to this point, this point to this point, and this point to this point in order to reach to this weight. You can see that you can check your chain rule also. If you'll see these, all these things will get cut out. It will cut, and you'll just have left with y cap upon dw121.
So Ashutosh, but this neuron which is between H2 and Y cap,
Hmm.
Y hat,
Hmm.
that neuron doesn't have any. It should have like H3 right there, or
Where?
no?
Which?
Before Y hat.
This one you're talking about?
No, on the right side.
This one?
No, the
Yep.
one between. Yeah.
Okay. Yeah.
So like we have H1 there, right? First, then
Yeah.
second we have
Here you
H2.
should, you're asking for some H3 you're saying?
Yeah.
Yeah, it can have H3. It can have. My point is not to give you the exact calculation. I'm just trying to
Okay.
explain
Okay.
you the chain rule, right?
Okay. Okay.
Okay. That actual calculation we'll see later. My only point is you understand the chain rule, how we compute, if we want to compute this loss with respect to this particular weights, we have to back propagate, right? You have to travel all the way back to this neuron, and you have to do something like this, and you can check whether your this chain rule is correct or not. If you will cross all these things, you will ultimately left with dl by dw1, and that is what we want to calculate.
Yeah.
Right? Yeah. So this is the theory part of it. Now,
But then these paths are from multiple places, right? Like one is from
yes,
top and other one will go from
yeah,
down, one will go straight, right?
yes. So for each possible computation, we'll do we'll we'll write equations like this. This is just one path I have chosen. Similarly, you could have gone from this point to this point, this point to this point, and this point to this point. Right? There's another possibility: this point to this point, this point to this point, this point to this point, and after that, you reach W121. Okay. See, it's really not really important how exactly this weights are and prices are getting updated. Keras will take care of that. But still, if you're interested, for that, I'm just giving a heads up that this is the way it happens at the back end. Okay, you'll see that all this theory part which we're saying, it is totally irrelevant for solving a problem, because we really not need to worry about this.
Okay.
Okay, I am going to send you another bridge, because only it has 10 minutes left, and I'm pretty much sure that in 10 minutes I cannot cover the hands-on session. So I'm disconnecting this call and sending you a new link. Please join that, and we'll see
Okay.
the hands-on part.